Question 25 first of all wants to know what happens to each of these substances when you reflux with aqueous acidic dichromate. So remember, that depends on whether they're primary, secondary or tertiary alcohols. This one is primary because the carbon with the OH has only one other carbon directly attached. And if you have a primary alcohol, remember you have two possible outcomes. You can oxidize first to the aldehyde, which would be this. But then if you oxidize for longer, that oxidizes further to the carboxylic acid, which is this. And because it says reflux, remember reflux enables you to oxidize for a long time because you keep returning the reaction mixture to the, returning the compounds to the reaction mixture in the vessel where they keep getting re-exposed to the oxidizing agent. So that is the correct answer for part A, because it's refluxing. B, that one's a tertiary alcohol, because the carbon with the OH has three other carbons attached, and tertiary alcohols can't be oxidized by aqueous acidic dichromate, so it tells you to write none if there's no product there. C, that one's a secondary alcohol, because the carbon with the OH has two other carbons attached. Secondary alcohols can be oxidized to ketones, which just changes that into double bond O, and that's as far as they can go. No further oxidation is possible, so that is the correct answer for C. So then it wants a couple of more things. It wants the systematic name for this alcohol, alcohol C. So you can see you've got a chain of 4 carbons, so it's bute. It's saturated because there are no carbon-carbon double bonds, so it's an. And then we're going to number the carbons starting at this end, because we want to keep the number as small as possible, and we're going to have a number when we get to this carbon because of the OH, so we're going to number it 1, 2, 3, 4, like that. So carbon 2 has the OH group, so it's butan 2-ol is the name of that compound. And then it wants the equation for complete combustion of alcohol A, which is this one, although in fact because they're isomers it would be the same for all of them, because it's inviting us to use a molecular formula, which is that for alcohol A. So complete combustion, remember, is a reaction with oxygen to produce carbon dioxide. That's what the complete bit means, that you produce carbon dioxide rather than carbon monoxide or carbon. So CO2, and then as always in combustion, water is where the hydrogens end up. So 4 carbons on the left means we have to have 4 CO2s. 10 hydrogens on the left means we have to have 5 H2O to give us the 5 lots of 2 to give you 10 hydrogens on the right. And then if we add up the numbers, we've got 4 2s are 8 oxygens there, plus another 5 gives you 13. So going over to this side, you can see one of those 13 is already there in the alcohol, so we need 12 more oxygen, and therefore that's just 6 O2. Make sure that you noticed that that one was already there. It's very easy to forget that, in which case you'd have got 6.5 there. Part B then is about the radical substitution of C4H10 when that reacts with chlorine. So this would be the overall reaction, substituting in 1 chlorine and forming HCl. But it's asking here for these steps in the mechanism. So the initiation step, remember, is just about breaking the chlorine molecule open. So the initiation reaction is Cl2 goes to 2Cl dot, where the dot, remember, represents an unpaired electron. So you're breaking open the chlorine molecule into 2 chlorine atoms, and that's what gets the whole thing started. So that's the initiation step, and the conditions you need for that are UV. Okay, that's the key thing you need to provide the energy to break that bond. And then propagation is where the main reaction happens. So propagation has 2 steps which follow each other in a chain reaction, and when you add the 2 steps together, it gives you the overall equation for the reaction. It's important to remember that that's the case, because then you can check that what you've written makes sense, because when you add the 2 together, it should add up to that. So the idea is that we have, now we bring our C4H10 into play, and it's about what happens when it meets the chlorine radical. And what you have to remember is that what these radicals tend to do is to grab an atom, right? Because it's got a hole in its outer shell, it's got a gap in its outer shell where an electron can be placed. It tends to grab an atom so that it can put an atom into that gap in its, put an electron into that gap in its outer shell. And if it meets a butane molecule, it's likely therefore to grab one of those hydrogens. So what that will give you is HCl then. And of course what it leaves behind is C4H9. And that's now a radical, because when the hydrogen gets taken away, it leaves an unpaired electron on the carbon. So we get C4H9 dot formed in that step. And so we still have a radical. That's the point, that doesn't end the story, because we still have this reactive radical here. So that then comes back down here to do its thing. And what it's going to do is again grab an atom out of what it bumps into, and if it bumps into a chlorine molecule, then you get this reaction. Gives you C4H9Cl, which is the other product of the reaction. And again, if it's taken one chlorine out of there, that will leave Cl dot behind. And that Cl dot then of course can go back into here, and so these two reactions can keep on following one another. So that's all you need to get the marks. But as I say, if you weren't confident you'd got it right, you could try adding all this lot together. So you get C4H10 plus Cl dot plus C4H9 dot plus Cl2. So all the things on the left hand side gives you HCl plus C4H9 dot plus C4H9Cl plus Cl dot. And that looks like a mess until you realise that there are a lot of things that are there on both sides and which therefore should cancel out. So the Cl dot is there on both sides, so that drops out. And the C4H9 dot is also there on both sides, so that also cancels out. And what you're left with is C4H10 plus Cl2 goes to HCl plus C4H9Cl, which is indeed the overall reaction. So you know, therefore, that those propagation reactions make sense because they add up to the correct overall equation. In part 2 then it's asking us, well, what if you don't just substitute once but you keep on reacting with chlorine until all of the hydrogens have been substituted, and so you're going to react with more than one chlorine to give you not C4H10 but C4Cl10. Well, what you have to remember is that because of the way that mechanism works, every chlorine that goes in produces an HCl as well. And you can't avoid that. Just because you could balance the equation without doing that doesn't mean that's what happens. So you've got to remember the pattern of the reaction, that for every chlorine that substitutes in, you get an HCl as well, and so you therefore get 10 HCl, and you can see that's 20 chlorines altogether on that side. So fairly obviously you need 10 Cl2. So that's the equation that you need. For this last part, we've got a situation where some but not all of the hydrogens have been replaced by chlorine. So if you like, we're going to get a product which is C4H10 minus X ClX. So we've substituted in X chlorines and therefore we've lost X hydrogens. So what we need to do is to work out the MR of this compound, and then we can work out what X needs to be in order to make it fit that MR. So the first thing is that it tells us that 0.636 grams has a volume equal to 78.0 cm cubed, but not at room temperature and pressure. So you can't use 24 because it doesn't say room temperature and pressure. But you don't use the ideal gas equation either because you haven't got all the details for that. What you've got is that under these conditions, the molar gas volume is not 24.0 dm cubed, but instead is 32.5 dm cubed. So you just use 32.5 in the same way you would use 24 and get that moles is equal to the volume in dm cubed divided by the volume of 1 mole, which is not 24, but 32.5. Okay, so it's just about being flexible and making sure you understand what you're doing when you use the 24 thing, so that if its conditions are different, so the molar volume is not 24, you can still work it out. So 78 cm cubed is 0.0780 dm cubed divided by 32.5, which is 2.40 times 10 to the minus 3 moles. Okay, so 0.636 grams is equal to that number of moles, and that lets us work out the MR, because the MR is mass over moles, which is 0.636 divided by 2.40 times 10 to the minus 3, which comes to 265. So we've got that the MR is equal to 265. So now we can just work out what X is. You could probably do it by trial and error if you don't like algebra. Well, I mean, you can do without too much trouble. You can just try it with, a few chlorines. So guess maybe 5 in the middle of the range, and then say, right, does that give you an MR that's slightly too big or slightly too small? And then you can kind of home in on it. But if you want to do it algebraically, you can, because you can get that the MR, 265, is equal to 4 carbons, so that's 4 lots of 12, is equal to 48, plus 10 minus X lots of hydrogen, so that's 10 minus X times 1, because the mass of a hydrogen is 1, plus X lots of chlorine, and chlorine is 35.5, plus 35.5 X. Okay, so that's just adding the masses of those things together. So if we reorganise that, that's equal to 48 plus 10 is 58, plus 35.5x minus x, so 58 plus 34.5x. And then if we move the 58 over to that side by subtracting 58 from each side, that gives us 207 is equal to 34.5x. And so 207 divided by 34.5, which comes out to be exactly 6, is equal to x. Okay, so that's the algebraic way of doing it, which is sort of the most elegant way, but if you hate algebra, as I say, you could do it by trial and error and that would be fine. So x is 6. In other words, the formula of the compound is C4H10 minus 6 is 4, Cl6 is the answer.